Will be a discussion total estimation of the total gas content. Okay. If you see yesterday's class, and we have seen that if you are going to do the estimation, then the problem is that you have to take the three components. First one is the dissolved gas content, then there is a lost gas content, and then there is a residual gas content. Okay, so if you are able to take these three component more or less accurately, then you will be very much able to do this estimation of the reservoir gas content very correctly. Okay, correctly. So, yesterday we have seen that what are the different procedures or what are the different aspects or step-by-step method that we can use when we are going to consider the dissolved gas content. And we have seen that depending on the core canister testing or from the pressure course or for the conventional disruption canister, will be able to do this dissolved gas content and with particular time. If we are going to put the time correctly, then only you will be able to measure or estimate the dissolved gas content, which is with the pressure. Okay. The most critical aspect with this three component, the dissolved gas, the lost gas, and the residual gas content, is obviously the lost gas. Because whenever you are going to calculate the dissolved gas content, you have some idea. Okay, you have some idea because you have established the isotherm, the Langmuir isotherm, and also you have seen that with pressure, what is the amount of the gas that is coming out. So you have some relation with the pressure and the adsorption quantity. Okay, so for any particular reservoir, if you can estimate the reservoir pressure, okay, then you will be able to estimate. And then for the accurate measurement, you have to take the help of the isotherm. So isotherm will give you just a guideline for accurately measurement of the gas adsorption isotherm. The second component, the lost gas component, is very tricky one. Why it is difficult and tricky one? Because when you are going to because the lost gas means the gas which is going to be elapsed into the atmosphere. Okay, so obviously if you are unable to estimate, you cannot actually measure it. Okay, so you have to estimate it, and then you have to estimate based on the time. Why time is coming in here? Suppose when you are taking your core barrel to the surface, okay, in the core barrel, the core is within the pressure of the drilling mud or the drilling fluid, and so it is more or less maintaining the reservoir pressure. Now, as you are going to take it up to the surface, the pressure is going to decrease because the H, if you consider the vertical stress, the H, the depth of the depth from the surface is going to reduce. So obviously, the stress or the corresponding pressure is also going to reduce. Okay. The point is that the moment you are going to take out the sample from the core barrel, okay, if you are not going to put the stopwatch, or more accurately, the moment you are going to take out the sample from the particular depth, suppose your coal seam is situated at the particular depth of the 500 meter. So when you are withdrawing the core barrel from this 500 meter, okay, if you see that there is a lot of pressure variation from the surface and the 500-meter depth pressure, then again some portion of the gases Hello, am I audible? Hello, can you hear me properly now? There was some disconnection due to slow internet connection. Can you hear me properly now?
Yes, sir.
Okay, okay. Sorry for this problem. So suppose that if you are going to, okay. So suppose that when you are going to take the sample and you are going to collect the sample from underground, okay, and then you are going to take out you are going to take out the sample from the underground reservoir to the you are going to bring it into the surface, okay. Now the problem is that when you are going to take out the sample and as you are going to take out the sample from the depth, okay, some amount of the gases will be starting to dissolve already. Why? Because the pressure is going to reduce. The point is that if it is within the core barrel, the gases will be also remaining intact into the core barrel. It will not be elapsed. But the point is that if you are unable to get the total volume and during opening, if you are going to release the gases to the atmosphere, if you are going to allow the gases to vent out into the atmosphere, then you are going to lose. Okay. So what you have to do? You have to transfer the core sample from the core barrel to the desorption canister test, where the test will be done, where you will be allowing the core sample to dissolve at the zero pressure. So you will be putting the desorption canister test fitted with a pressure gauge so as to monitor the pressure, and then as quickly as possible you have to transfer the core sample from the core barrel to the desorption canister test. And at this point you have to put a stopwatch so that you can take the zero time. Zero time means the starting of the desorption as we are going to conduct, because even if you are going to collect this take the sample from the underground to the surface, as there is a drilling fluid pressure, so more or less the reservoir pressure is also maintained. Okay, there is not much variation. But the moment you are going to open it, the drilling mud has to be taken out, so the pressure is directly going to zero, and then the gases may comes out and gas may comes out and it can vent out to the atmosphere. So that's why, to reduce that thing, what you have to do, you have to put the sample into the canister, but before that you have to put a zero clock. Okay, and if you see the text, okay, they have given here some equation, which is, if you see this equation, these equations are obviously going to be important and going to be dominated by the diffusion characteristics. You can see that there is a term of root over d by r square. This d by r square is the diffusion coefficient, okay, and r is the radius of the particle size of the gas. Okay, r is the radius of the particle size of, not the gas, sorry, it is the characteristic diffusion distance of the sample. That means it is a sample radius. Okay, and the way it is moving from the pore wall boundary to the surface, to the empty to the cleavage fracture surface. Okay, because after diffusion only it will be coming to the fracture surface from the pore wall boundary. So this diffusivity or the diffusion coefficient is also greatly affected by the time. Okay, and this diffusivity is related to the rate of adsorption. This diffusivity or the diffusion coefficient is related to the rate of adsorption. That means how much or how quickly or how slowly the gases are going to be adsorbed or dissolved from a particular sample corresponding to a particular temperature and pressure combination. Okay, so that's why this parameter is going to be very much important. And if you see this graph in detail, this graph is very important, and let me tell you that this process of calculation of the or the estimation of the total gas content with these three components you have to understand very clearly. Okay, so what is happening, that whenever you are going to plot the gases with the square root of elapsed time, you can see in the x-axis they have taken square root of elapsed time since the start of desorption, which is plotted in hour, root of time, okay? And then there is a cumulative dissolved gas content in SCF per ton. From where you are getting this graph? The moment you are going to put into the desorption canister core sample, in the pressure gauge, the gases will be started to dissolve, and so the gases will be accumulated into the desorption canister void volume. Okay. After some time, when the gas pressure is going to rise up, it is totally filled with the gas. Now, again and again, if the gases are going to dissolve, so obviously it is going to give rise of some pressure. So that pressure will be notified by the pressure gauge. Okay, that pressure will be notified by the pressure gauge, and obviously, whatever slope you are going to get, you can see that previously there is a steep incline slope, linear slope, more or less. Okay, and then as the time goes, the desorption will be reduced because of the content of the gas, and then you will be seeing that there is a flat graph, so no pressure increment or the no gas increment is there. So then you have to understand that whatever the desorption is needed to be take place, it is already done. So total desorption from the core sample has been streamlined, so it is reached an equilibrium state, so no further gas desorption is possible. Okay. But in this case, if you are going to observe the situation, that whenever you are going to see these two part, the first is the inclined part, this is the linear part. Okay, the linear part, and then let me increase the resolution of the figure. Yeah, this is the first part is the linear part when it is increased continuously in a linear fashion, and then it is going to be streamlined. Okay, going to be flat. So this much point you have taken, you can see there they have put the sample in the canister. Okay, this is the point, and this is the sample heating period. That means whenever you are going to put the sample into the canister, so the sample is taking the temperature of the ambient atmosphere. Okay, that means in the reservoir the temperature condition was totally different. It may be less temperature or it may be increased temperature. Okay, depending on the seasonal variation, and even if there is a geothermal gradient. Okay, have you heard about the term called geothermal gradient in your environment class? Geothermal gradient.
Yes, sir.
Okay.
Yes, sir.
Geothermal gradient is giving you the idea that if you are going to the depth from the surface, how is the increment of the your temperature. Okay, and this is varying from place to place. For running and cold field, it is just 38 meter for 1 degree. Okay, approximately 40 meter you have to go for 1 degree increments. Okay. So if you see this graph carefully, you will see that they have put the sample into the canister at this point, and they have put the stopwatch as 0. Okay, and then they are going to plot. So at this time, okay, this is the time, and the gas production just started. Okay, so the gas production, you can see that it is 0, but see, the time is not 0. Why? Because the time should be put the 0 when you are going to open the core barrel, because that is the point where you are actually going to reduce the pressure to atmosphere, and then the gasization process is actually started. Okay, so that will be the point 0, but you cannot take that point, so you are putting the 0 by stopwatch so as to estimate. So you have put the stopwatch, and then you know that when you are going to put the sample, the theoretical gas production is going to be 0, and then it is going to be increased. The gas production is going to be increased in a streamlined fashion, in a linear fashion. But then as the gases are more and more gases are coming out, you can see that the cumulative production is going to reduce, and finally it is going to reach a straight line. Okay, so this is your dissolved gas content from this whole sample. But then you have to take the lost gas content. So for that, what you have to do, whatever 0 point you have taken, now you are going to backward to increase the slope, and to see in what point it is going to intercept the gas disruption graph or the dissolved gas content graph. Okay, so if you put the back side of this graph, okay, then you will see that it is going to intersect as approximately 250 SC per ton for this particular gas. Okay, so you can see they have put that arrow that the loss gas content estimate. This is very sensitive about the graph, about the way you are going to take out the putting the sample and taking the experiment. Why? Because you can see that if the slope, if the points are little bit, or the if the line what you are drawing, okay, if the slope is little bit changed, so suppose it is not going in this fashion, it is going to get with connecting of this first point and then it is going to intercept at this. So you will be getting nearly 150. This is minus because it is lost. That's why they have plotted in the minus. Okay. So, you can see that here you are going to estimate the loss gas as the 150 only, 150 SC per ton, whereas it is actually 250 if you are accurately going to monitor the sample. So this is the problem, that the lost gas is very accurately to be estimated. Otherwise, it is very much sensitive to the temperature. It is very much sensitive to the time. The starting time when you are going to put the zero, that is the most crucial point. If you read the text, if you go through the text, okay, you will see that they have discussed this point again and again, that initial point, this is the starting point, and this point you have to monitor very accurately. Okay, because if this is the time scale, you can only know that okay, this is the elapsed time. But if you are not going to record that when there is a zero time, so from 1.0 or from 1.2, you will not be able to going back. This is coming as 1.2 because you have put 0 in earlier. If you are going to put 0 the moment you are going to put the sample into the sealed canister, sealed means it is closed canister, okay, so that there is no leakage. Okay, if you are going to start 0 here the time, then obviously you will not be able to get the lost gas content, as if you are going to start the gas content, you are going to start the deduction right now and there is no lost gas content, which will be wrong. Do you understand this situation? Do you understand the graph now? It is very important, okay? That the defined procedure, the step-by-step procedure we are going to consider for lost gas scenario, it is very important to understand, okay? So that's why if you see the measured data, okay, the points are going to give you the measured data which is plotted based on the graph, based on the readings you are going to take from the stopwatch and the disruption canister gas volume, okay, whatever gases you are going to collect. But then when you are going to fit the straight line you can fit with the slope or the linear slope, but then how far you are going to extend, whether you will be extending in that point, up to that point, or this point, or maybe at this point, or maybe later than this is going to give you the idea about the loss gas content. Okay, so read this part carefully. In the text they have given the description about why this is so important, how you are going to estimate the loss gas. Now, having to understand this concept, you will again see that there is various parameter. Just like the temperature, the pressure is obviously a parameter. The temperature, the handling of the sample, okay, the way, the time you are going to take to remove the canister, remove the core barrel and open the disruption canister and putting the core barrel into the disruption canister. So all this time elapsed, you have to reduce the time. Until unless you are going to reduce the time, until unless you are going to monitor the time, you will not actually going to estimate the lost gas content. And believe me, this is the most crucial because you cannot measure it directly. Okay, if you see the slope, this slope is obviously the rate of disruption. This slope, this linear slope, and this asymptotic graph is obviously particular to the particular coal sample or the particular coal seam, okay, or the particular coal core which you have taken from the underground. Now this part will vary from coal to coal and from different location, from different depth. because it is totally heterogeneous. Okay, coal is a sedimentary rock. It is totally heterogeneous type of rock. Although for the modeling we are going to consider that it is a continuous, homogeneous, isotropic and linearly elastic, but in actual field process it is not. It is a rock mass, so it will never behave isotropic way. Okay, so it is very much anisotropic. So again you need to understand that this slope is going to be vary for different oil sample. Okay, if in the next part, if you are going to consider the residual gas content. What is the residual gas content? If you remember, we have discussed about the three gas component. Okay, the first one is the dissolved gas component, second one is the lost gas component, and the third one is the residual gas component. Okay, now the residual gas means if you have studied the isotherm characteristics. In the isotherm characteristics there were 2 points. Okay, if you remember, the first one is the critical resorption pressure. Okay, beyond which if you are going to reduce the pressure beyond the critical resorption pressure, then only the desorption condition will arise for the particular coal and gas or the particular coal bed reservoir. Okay, if the gas reservoir pressure is more than the critical desorption pressure of that seam or that coal sample, you will not be able to get any gas desorption, or you will not be get any gas production. And again, this critical desorption pressure is fixed for any reservoir, but then depending on the whether the reservoir is saturated or partially saturated, okay, this desorption pressure will give you the gas production, or it may not be give you any gas production. Okay, so the moment you are going to take out the water from a reservoir, suppose that it was totally saturated. Suppose that it was totally saturated with the gas at that temperature pressure condition, reservoir temperature pressure condition. So what will happen? As the coal is totally saturated with the gas, so the moment you are going to reduce the pressure, okay, as this is totally saturated, so obviously the moment you are going to reduce the gas pressure, you will see that the some gases are coming out. Why? Because it is totally saturated and you are taking out the water, gas pressure or the pore pressure is going to reduce, so gases are going to dissolve. Okay, so in that case the critical desorption pressure will be same or maybe much higher, because you don't know at what percent the saturation is there. Even if you can only understand the critical desorption pressure if the reservoir is partially saturated. Okay, and in the lower limit, when the critical desorption pressure has reached and the gases are starting to production, you have seen that the gas nature, that the isotherm nature is going to change from the very flat to continuously inclined. Okay, and as you are going to reduce the pressure much more, then the graph is becoming quite steeper. Okay, if I show you the graph, if I show you the isotherm graph you have seen earlier, let me show you again. Yeah, suppose, okay, suppose this is your isotherm. Suppose we are taking pure carbon dioxide graph for the isotherm. Okay, so what will happen if you are going to reduce the pressure? Okay, so you will continuously get that it is flat. So as much as you are going to reduce the pressure, you are not going to get that much proportionate gas, because to reduce the gas pressure from 1000 to 800, you have to come from this point to this point. But how much gases you are going to get with this pressure reduction from this point to this point? Only maybe some 50 SCF per ton, because the graph is more or less flat. But as you are going to reduce the gas pressure, by taking out the water, you can see the graph is becoming steeper. So imagine the situation is going here. As you are going to reduce the pressure from 400 approximately to 300, okay, you are going to get gas production from suppose 625 to 600, so 25 or even some 30 or 35 SCF per ton. Again, as you are going to come to this very much lower pressure, so then you can see that if you are going to reduce the pressure from 200 to 100, you are approximately going to get a gas production of 500 to 400. That means now in this stage you are going to get 100 SCA per ton. And these are, remember that these are all the stage adsorption. Okay, I am going to consider this stage as in this graph they are going to plot the cumulative one. Again, you know that there is a point which is called the abandonment gas pressure. Abandonment gas pressure. Okay, and there is a term which is called the abandoned gas content or the abandoned gas quantity. What is that? If you are going to reduce the pressure, you cannot reduce the pressure directly to zero. There will be some earlier steps. Suppose when you have reached 100 psi absolute, you can see that the x-axis they are going to measure it as psi absolute. Absolute means the gauge pressure, the pressure at that particular point of the depth plus the absolute pressure, the 101.32 kilopascal. Okay, so whenever you are going to reach suppose 100 or 150, you will see that you are not going to get, you are not going to reduce the pressure further. Why? Because the pressure reduction is accompanied by the water taking out. You are taking out the water, but then remember, if you are remembering the concept, then there is a mobile fluid, there is the immobile fluid. Okay, so whatever water that are mobile, that you can take out, but there is always some part of water or some part of moisture which is inherent to the reservoir, and that you cannot take out, and that water pressure will be always present into the reservoir. That water content or that water saturation is always present within the reservoir. It may vary from reservoir to reservoir, from different type of places or different type of coal sample. Okay, so suppose that for this particular graph, you are unable to get any data below this 50 psi. So we can say that 50 psi is the abandoned gas pressure or abandonment gas pressure. Okay. So you will not be able to get any gas output below this pressure. So this particular pressure is called the abandonment gas pressure because the gas production is abundant. Okay, gas production is abundant, so no further gas production is coming up. So what you can see that although some maximum part of the gases are going to dissolve, there is also some part of the gases which are trapped because you are unable to reduce the pressure from 100 or suppose 50 to 0. This part of the gas which is already trapped, you have to take out. You need to take out this also to get the total gas content of the reservoir. So what you are going to do, suppose you are going to take a coal sample, you are preparing a coal core and you are going to apply the gas injection into the laboratory, and you have followed the gas injection and you are going to take out the gases, but then you will see that some part of the gases is already will be there. Okay, beyond abundant gas content, okay, beyond abandonment gas pressure. So what you are going to do, the residual gas content, if I am going back to the your original discussion, let me going back to you. So the residual gas content is going to give you the idea about how much residual gases are trapped into the coal beyond the desorption limit. The residual gas content will give you the idea about the gases trapped into the coal beyond your desorption limit. That means beyond your abundant gas pressure, whatever gas pressure is already there into the reservoir, how much gases are already trapped, which you are unable to get by the desorption process. So that part is to be measured by the residual gas content. Okay, how you are going to measure? Suppose you have taken the sample, you have reached abundant gas pressure, you have taken desorption answer testing, and you have got a isotherm graph. You have also taken out the lost gas connective connection, and you will be able to estimate the lost gas. Okay, but now if you have seen that from the desorption canister that the gases has reached the flat line, so no more gas production is allowed. Okay, that means if you see this graph, if this is becoming straight line, if this gas production from the desorption canister is becoming straight line, then you will see that no further gases are coming out by desorption only. But then what you have to do, you have to take this point so that you can manage whatever is the loss gas. And now you are going to open the dissolution canister, you are going to take the coal sample, you are going to break the coal sample in a closed container into the small lumps, and then you will see that some amount of the gases will be coming out. Why? If you are going to crush the coal sample to the small lump size, what you will get, as you are going to break the chunks or the lump size of the coal, what you are doing, you are actually increasing the surface, the contact surface, or the surfaces from where the desorption can take place. So as you are going to break the sample, okay, you are going to you are going to crush the sample, so its pressure, okay, some amount of the gas pressure is going to be reduced. Okay, the more and more breakage you are going to do, okay, so when you are going to crush the sample to some mesh size, okay, you will see here in the residual gas content they have also provided that the residual gas content is determined by measuring the gas released from the core sample after crushing to a minus 20 mesh particle size in a sealed ball mill. So I hope you can understand. The minus 20 mesh size means the undersize of 20 sieve or 20 mesh. US mesh number 20. I have shown you earlier what is the mesh number, and undersize means the lower part. Okay, the lower part means the smaller size fraction. There is the undersize, there is the oversize. So you have to collect the undersize. So whatever coal size you are going to produce by crushing, the gases coming out from the coal sample which is prepared by crushing with a size fraction of minus 20 mesh particle size, at that fraction only whatever gases are coming out, that gas amount will be considered as the residual gas content. Okay, so now you can understand that depending on the core sample you have taken, there may be a very significant, because depending on the smaller particle size, the desorption of the coal core is very less. The rate of desorption, like the diffusion or the adsorption rate, is also very less for the coal core sample. Why? Because the surface area exposed is very less. But if you are going to break the sample, you are going to crush the sample, and you are going to produce the lump size or the smaller size fraction like the 22, yeah, or else it may be under minus 100 to 150, then you will see that a lot of gases which are earlier it was trapped, now the gases are coming out. Why? Because each particle are now exposed to the atmosphere, and so the surrounding surface, the contact area, okay, is also increased, and with that contact area the sample is going to diffuse and coming to the open fracture system, and that's why you are going to get the production. It is observed in the laboratory experiment also and in the field studies also that whenever you are going to get the desorption canister test, after desorption canister test, when you have estimated the lost gas content and you have measured the dissolved gas content, and when you are going to measure the residual gas content, significant amount of the residual gases are coming from the broken rock. Why? Because as you are going to crush the sample in under 20 mesh size particle size, so in the sealed ball mill, so obviously when the coal surfaces are getting reduced, the size fraction is going to be reduced, the gases will come out, and if you are going to collect those gases, this gas amount will be considered as the residual gas content. So now if you have taken three different amounts, first one is the dissolved gas content, then the lost gas content, and then the residual gas content. So summing of these three will give you the total gas content of that coal, or the total gas content from that sample only, not from the reservoir. You are getting, because you are going to measure the coal sample, the core sample. So whatever gas content for this stage, it is actually for the total gas content that is coming from that coal core. Now with that coal core, okay, you are going to estimate, you can may estimate this for the reservoir also, because obviously you cannot take the total core sample from all the places and you are going to estimate into the lab. So you have to estimate based on the total area, based on the coal properties, and based on the some density parameter, or some fraction about how much gas content is coming. Okay. So if you see this table, in this table they are going to tell you that what are the different gas content you are going to get from different method. Okay, so you can see that you will not be able to get that loss gas analysis from the pressure core or the sidewall core. Okay, but then if you are going to represent it as the different basis, then there will be some differences from the same coal type. There may be some differences about the total gas content. You can see that the correction, there is a range of the accuracy. Okay, and so you will be able to get various results. So you need to understand that every test is for different purpose, is for different stages, and for each different stages you have to be very much careful, otherwise your results will be too much scattered. Okay, now when you are going to estimate the in situ gas content, okay, when you are going to get the in situ gas content, what you are going to do, you are going to get the predicted gas content from the coal core, and then you are going to, suppose for the predicted gas content, if you are going to consider the whatever gas content you have calculated, you are going to give the subtract the moisture percentage and the ash percentage, and then finally you are going to get the predicted gas content. Okay, in DAF basis, dry ash free basis. Okay, SCF per ton. So this way we are going to get estimation of the total gas in place. Now here, if you see this, as you can see this graph, that relationship between the core sample by direct method of the total gas content and the non-coal content. So you can see that if you are going to increase the ash and moisture content, obviously the dry gas content is going to reduce. Why? Because obviously the ash content is going to block the carbon content. Okay, the more and more ash content will give reduction to the carbon content. Okay, and the ash is not going to store the gases. Okay, it is all the coal or the carbonaceous matter. Similarly, for the moisture is actually going to block the pore spaces which may be available to the gases. So if you are going to increase the moisture percentage, again the gas content is going to be reduced. Now here they have done some statistical confidence interval testing. You may have the idea about the various hypothesis testing like t-square distribution, t distribution, t-square distribution, or f distribution, or chi-square method. Okay, do you remember this statistical distribution? Some of it. Do you remember
Yes,
the
sir.
names? Okay. So
Yes, sir.
what you are going to do? Suppose you have got a result, but then you have to show that how much accurate are those results. So you have to take the hypothesis, and with the normal distribution graph, or maybe the chi-square distribution, or t distribution, so you will be able to put that, okay, with 95% confidence interval, I am reporting that this reservoir is having this much of the gas content. I have given this, you can see this is the 518.7 is the actual, plus minus 30.7 is the error, the standard deviation. Okay, what you can say. And then the confidence interval graph. The confidence interval graph is also taken from this hypothesis analysis. Okay, the population analysis. Why this is given? To give you an idea about the how much accurate your data, and to provide a range other than just mentioning a value. Okay, so this is the way we are going to calculate the total gas content. And obviously, suppose you have taken some sample and you are going to provide it SCA per ton per unit weight basis. So again, if you are going to consider your coal seam, and if you are going to consider the total volume or total weight percent of your coal seam, and then you are going to reduce the ash percentage and the moisture percentage, and you are going to multiply that with this gas content, okay, whatever you have calculated, so obviously you will be able to estimate roughly, you are going to be estimate about the total gas content or the gas in place. Okay, so this is the steps, these are the steps. Okay, now to do this actual gas in place, I have to skip some of the discussion because it is not that much important, but at this point, yeah, there may be some difficulty for you to understand, but when you have studied the total parameters, then if you are going to read this text, it will be easy for you. Okay, so I'm just skipping some of the points, only those which is very much useful to you I'm going to discuss. Okay, now in this graph, suppose I have told you that total gas in place calculation is very important. So suppose how much dense is your reservoir. Suppose to get the density, we are going to collect the sample and then we are going to measure the density in the coal sample in the laboratory analysis. But then if you are going to estimate the total density, the coal seam density of the reservoir, how we are going to estimate it? Suppose this is the signature, this is the for various depth. These two table you can see, just to continue the earlier discussion with depth. This is the depth, this is for the same depth, okay, 2435 to 2453, this is also 2435 to 2453 feet. Okay, so at each depth they have got the different ash content like this. This is the data, and the block point is that the blocks or the icons are giving you the idea that they have actually taken the coal sample. You can see that the various separation distances are there. They have actually taken the coal sample and they have analyzed, they have measured the ash content, and other they are derived the results from the log derived estimate. Log, the borehole logs, okay, they have done the estimation. Or sometimes you must have heard about some gamma ray or the resistivity logs, from where you can get the idea about the density, about the density and the other elements. Okay, so if you see this data, you can see that with depth there's a lot of variation of the ash content. Why? Because obviously this is a coefficient process, and the coal, depending on its location, depending on its grade, rank, and composition, obviously this content is going to vary from place to place. Okay, so you can see here that within a 15 meter of depth, 15 meter or 18 meter depth, how much it is going to vary. Okay, again, corresponding to the ash content, okay, you can see that if the ash content is very less, you will be getting the gas content very high. So for these values where you are going to get the very low ash content, at this depth you are going to get the very high gas content. Okay, these are just to give you some idea from the field data. Okay, if you want to read it directly, I'm just going to give you the results. You please read once, at least once you try to read it carefully, and then you will be able to take care of this. Okay, now our more or less final discussions for this storage is for the reservoir thickness. How we are going to know about the reservoir thickness? Now there are two type of thickness. One is the gross thickness, which is the actual thickness of the coal seam, and then there is a net reservoir thickness or the net pay thickness. The net pay thickness is the actually the amount of the zone or the amount of the thickness of the coal that is actually going to be used for the CBM production, or that is actually going to give the production, okay, and helps the production, gas production. So how we are going to get the thickness? You know that being a mining engineer, whenever we are going to prepare the borehole exploration, we are going to get the borehole logs. Okay, there are various discussion, they have the method, different method they have applied here, but in a nutshell, let me give you the idea that the borehole logs, okay, Even if you are going to mine, even if you are going to see some mine plan, you will see that there is a cross section of the boreholes are given, a particular borehole. Okay, and in the borehole you will see that from the surface how much depth you are going, and with the depth, with proper thickness, there is a proper zonation of the different rock type. So from there you can easily get the thickness. Okay, other than this, suppose when you are going to drill, okay, depending on the variation of the drill speed, okay, or drill penetration rate, obviously you will be able to understand, obviously the driller, the operator will be very much able to understand this, because actually he is applying the pressure, he is actually controlling the drill bits. Okay, so the penetration rate, depending on the penetration rate, if you put a graph of the penetration rate with the time, then obviously you will be also going to get some data, because you will see that there will be a lot of variation. At the soft strata, the penetration rate will be much higher, but at the hard strata, the penetration rate has to be very much controlled, very slow, otherwise there will be damage of the drill bit. Okay, if you see the discussion, they have also mentioned that there are certain parameters which is going to dominate the drill penetration rate: the structure, the borehole position, the drill bit, the type of the coring meat, the rotational speed, the main power of the equipment. Okay, there's so much conditions, but then also from this drill penetration rate, you will be able to take some idea about what is the strata condition, or what is the different type of strata. Then comes the net reservoir thickness. That means the actual thickness which is going to give you the production is from the resistivity log. This is going to give you the accurate measurements. You have studied about the geophysical exploration or the borehole exploration. There are some magnetic method, the gravimetric method of the exploration. Do you know all of this? You must have studied this, right?
Yes, sir. Yes,
Okay,
sir.
so if you have studied this signature, you will be able to understand that with the gamma ray and with the density log, this how these things are related, or the seismic interpretation. These are called the seismic interpretation. You are going to get some P wave or S wave. Okay, you are going to get a signature, or you are going to send it, and then depending on the soft strata or the hard strata, it will take some different time, and it will give some amplitude or the give some density value. Okay, and then from there you will be able to estimate that with these values, that okay, what type of material it is. Okay, now here in this graph they have considered the lesser value of the density from 1.75 gram per cc. For coal, the coal density is 1.1 to 1.4 gram per cc. Okay, and so any density which is coming beyond or greater than 1.75 gram per cc, they have excluded this. That means there are too much mineral content, or there are too much rock content. So the depending on that, the gas content will be very less. So they are not going to consider that. Okay, and sometimes the block, the density of the coal block and the density of the powdered sample is little bit differentiated. Okay, if you are going to crush the sample, the loose rock density or the broken rock density is sometimes higher than the normal coal density. Okay, so based on these acoustic signatures or the seismic interpretation, you will be able to see that okay, what are the different layers, and even if there is only coal layer, what are the different signature are getting, and what are the estimated thickness from this graph. Okay, and then they have also given some case studies which is not required at this point, but they have given some data also. So if you see this data, you can see this how we are going to collect the sample or collect the borehole exploration, and how we are going to interpret the report. Okay, how the reports are generated and how we are going to interpret the report. So you can see this is the method they have prepared from the field study. They have taken that the coal which is below 1.7 gram per cc, these are going to give the production log. So they are going to get this type of signature. Okay, the gamma ray signature they have got this, and with the gamma ray signature they are going to estimate the density with the depth. Okay, so you can see that in this total range of the depth, they have considered only three zones. Only three zones. One is linearly, one is around 3150, one is around 3330, okay, and the third one is around 33 maybe 3370, okay. And with these three zones, they have estimated that how much gas production is possible. You can see that 37% is from the upper one, 11% is a very less one from the middle one, and the 52% is the lowest one. So totally it is going to give you 37 plus 1 11 48 and 52, it is 100%. So in that borehole production, they have considered that this way these three zones they have identified, and with these three zones they are going to get the gas production, okay. These are the possibility of the original gas production or original gas in place, okay. The next part, the gas control, the properties that control the fluid flow will be started after your examination. So any questions? For any questions from anyone?
Sir, these data are from a particular place now, sir. We cannot generalize this now.
No. I'm just